Hello and welcome back to Machine Learning video series. In the last video, we have had a look into regression problems and cost function. Now, let's look at another method applied in machine learning called gradient descent. Now, let's assume a square function of the form ax squared plus bx plus c and plot it on a graph. We will find that it is an upward-facing parabola. We can easily see that the minimum value of any squared function is when the parabola is flat with respect to x-axis. The laws of calculus dictate that differentiating a function gives its slope at any point. And we know that at minimum cost, the slope has to be 0. So, if we differentiate the cost function with respect to w and b, then equating it to 0 will give us the value of w as well as b. Because we have cost function in terms of both w and b, partial derivative of cost function j is calculated with respect to w and b separately, and then both derivatives are equated to 0. These values of w and b are added to the previous values. In training, to actually generate accurate predictions, this process has to be repeated such that cost across the entire dataset is minimized. Hence, we will get a value of w and b such that wx plus b minus y is minimum for any pair of xy values. This method of differentiating the cost and updating parameters to increase the accuracy of a model is called a gradient descent because our cost function descends down the parabola as we train our model. Now we know that we have to update the value of w and b, but we will not just add the calculated value directly. There will be a lot of fluctuation in our cost function if we do so. We would want to normalize the effect of each data point on our updated parameters. This can be done by multiplying a value to the new value before subtracting it from the previous value. So we can control how each new data point affects our weight and bias. So the update equation becomes this, where alpha is the learning rate. The learning rate is decided by the programmer. Setting a proper learning rate is a very important step. Let us consider 3 cases. If the learning rate is too low, every data point that we supply has a very low effect on the updated value. We had seen that we want the cost function to be on the lowest point of this parabola. With too low learning rate, every iteration will make a very small step towards the global minima. In the worst case, our data may not even be enough to reach the global minima with a value of learning rate that is too low. With an approximately right value of learning rate, the cost function will reach the minima at a decent rate with just enough number of training samples. But why don't we just keep a high value of minima? It might seem like a high value will make our model converge to the minima with low number of training samples. But this is actually worse than having a low learning rate. With a high learning rate, the cost function might overshoot from the minima and actually climb up. Hence, it will never actually converge and we will not even get a trend of the cost function. Our model cost will start misbehaving with a very large value of the learning rate. To get a better intuition of the learning rate, imagine a ball that is kept at a height on a parabola-like surface. If we drop this ball, it will go down. If it is just let go, it will arrive at the lowest point and stop. This is the best possible case. The training will take minimum possible resources and will have low cost at the end. If we set a learning rate too high, it is more like throwing a ball instead of dropping it. If the speed is too high, the ball will overshoot and climb the curve from the other end. Hence, we won't get the minimum cost. Moreover, we cannot even judge how the cost function is getting affected because it will keep increasing and decreasing, similar to how the ball will keep climbing up the curve and then dropping down. Hence, a high learning rate value can really be problematic. The third case is that of a very low learning rate. This is like holding the ball and not letting it go down. With infinitesimally small steps, the ball will take forever to reach the minimum point of the curve. This will not only take time, but will also require a larger dataset than what would have been required with a good learning rate. Complex machine learning problems already require datasets in order of gigabytes that are difficult to collect, store, and process. We would not want to consume more data or time than is required. This was gradient descent. It is one of the most used models in machine learning to minimize the error and get a really good prediction. You are not required to go into the maths behind the model. All you need to know is that there is a learning rate which has to be optimized and some basic theory which will help you while talking to a programmer if you are ever involved in implementing a machine learning model. This is all for this video. Thank you.